Hi guys, my name is Vivek and in this video tutorial we are going to talk about index organized table. Let's understand what is the basic difference between a normal relational table and an indexed organized table. The basic difference lies in the way the data is stored on disk. A normal relational table is heap organized. That means every time a new rows enter the table, it is inserted wherever it can fit. While in case of IOT, the insertion of a new row can lead to rearrangement of existing rows. And guys, this is very important. Focus on the word rearrangement. In a normal relational table, once a row is inserted, its physical location usually does not change, which is not the case with indexed organized table. The vital thing to remember here is that IOT is a variation of BTree Index structure. And this may sound a little confusing right now, so let's understand this in detail with the help of multiple examples. Here we are creating a regular relational table that has two columns, ID and name, and ID is a primary key column. Now let's insert three rows into this table. So as soon as we execute the first statement, Oracle allocates a segment. And guys, if you don't understand what is a block, what is extent, what is segment, what is splitting and spawning of index in Oracle, then I highly recommend that after the completion of this video, you watch my previous video on indexing and then come back and watch this video again. You will get a better understanding of the entire concept. When the first row is inserted, we have 1 and Vivek on the disk. Now when we insert the second row, we get 3 and Vishal. Eventually, finally, when we insert the third row, we get 2 and Vikram. Now notice, even though ID is a primary key column, there is no rearrangement because it's a regular relational table. So when I will go ahead and query this in the database, I will get 1, 3, 2. No rearrangement happened, and this justifies our first statement where we said that in a heap organized table, data is inserted wherever it can fit. So although we have ID as a primary key column, still we see 1, 3, 2, Vivek, Vishal, Vikram. Let's understand how IOT is different. So we have created a table IOT1, and when you add the syntax organization index, Oracle knows that it needs to create a indexed organized table. The important point to note here is that an indexed organized table must have a primary key. You cannot create a IOT table without the primary key. Now let's try inserting the same three rows. When we insert the first row, Oracle allocates a segment, inserts the row 1, which is 1 and Vivek. The next time when we insert 3 and Vishal, the same row is inserted again, 3 and Vishal. Now when I try to insert 2 and Vikram in a heap organized table, it was inserted after 3, but that is not the case with indexed organized table. It will push 3 down and will insert 2 in between 1 and 3. So this is how the output is going to look like. It is going to insert 2 first and push down 3 down. So when we are going to query the data, we will have 1, 2, 3. That means the data has been physically sorted on the basis of the primary key. Let's build a little further and understand what exactly happened. So if you remember, our normal relational table has ID as a primary key column. So when we insert our first row 1 Vivek, Oracle allocates 2 segment. So if you define a primary key column, Oracle automatically generates a unique BTree index. So a BTree index segment is created and a segment is created to store the data as well. So as soon as we insert 1 and Vivek, this is how it's going to happen. A row will be inserted in the table segment. That particular row will contain the values 1 and Vivek. Along with that, it will have a row ID, which is the physical location of the row. Oracle will also maintain an index that will have the ID 1 and the physical location where the row is stored. So as soon as we inserted 1 and Vivek, a row was inserted in the table segment and a corresponding index was maintained. Now when we insert 3 and Vishal, the same thing is going to happen. A row will be inserted here in the table segment and its corresponding address along with the ID will be maintained in BTree Index. Now when we insert our third row 2 and Vikram, the same thing is going to happen. The row will be inserted in the table segment, and since it's a normal relational table, the new row will be inserted after 3, but the BTree index should be maintained in a sequential order. So Oracle is going to perform a swap and the position of 2 and 3 will be interchanged. The most important thing to note here is that the physical location of the rows in the table did not change at all. Only the index was rearranged so that it can come in sequential manner, but the location of table data did not change at all. The row ID was persistent. And while we had two different segments for a normal relational table that had a primary key index, it is different in index organized table. And when we insert our first row in the indexed organized table, we see that we have only one segment, and that is BTree index segment. So guys, we will see this in action. When we create an index organized table, a single segment is created and that is for the BTree index. When we insert our second row, that is 3 and Vishal, it is inserted after the first row. So now we have 1 Vivek, 3 Vishal. Now when we try to insert 2 and Vikram, since it's an indexed organized table that has just one segment, BTree index segment, and as we saw in case of BTree in a normal relational table as well, that the BTree should be aligned in a sequential order, the new row 2 and Vikram will be arranged in between 1 and 3. So this is how the data will be stored. We will have 2 and Vikram inserted and then the locations will be swapped. So we will have 2 and Vikram between 1 and 3. Let's see how a normal BTree index is different from an indexed organized table. So if you have seen my previous videos on indexing, you will know that a BTree index has two types of blocks, leaf block and branch blocks. So these blocks right here that have only the pointers to the leaf blocks are called branch blocks. They provide the navigation path to the particular indexed key, and in the leaf blocks which are contained in this particular container, we have the primary key column along with the row ID where the row is physically stored in the table or the disk. So in a normal BTree index, we only have the indexed column value along with the physical location of the row, which is why we have two segments. The first is BTree index itself and the second segment is the physical location where the data is stored on the table. In case of index organized table, we only have a BTree index segment. That means in the leaf block itself, the entire row data is stored. For example, we have a table that has 3 columns, ID, name and salary. You see that the entire data is stored in the leaf block itself. So when we query an IOT table using its primary key, it only has to access this segment. In our normal relational table that has a primary key, if we try to run this query, select all from employee where ID is equals to 1, we have to do 2 IO operation. Initially we have to scan the index and then we will do a table access by index row ID. This is not the case with IOT table. We only have to do one IO operation since the data is stored on the index segment itself. While this may not look like a big gain right now, imagine this query running for 1,000,000 times during the day, and then the gain would be substantial. Also, in a normal relational table, we were maintaining the indexed columns at 2 different places, which is not required in IOT tables. Hence, IOT tables are storage optimized as well. And guys, these are the 2 main advantages of IOT table. They actually help in faster retrieval of data, and when you have a composite primary key that occupies a lot of space, you can consider choosing IOT table. They can bring down the storage space occupied by the object significantly. Let's quickly validate whatever we have already discussed in SQL Developer. So I'm going to create my normal relational table, regular one. The table has been created. I'm going to insert the 3 rows. So notice I'm inserting 1 first, followed by 3 and then 2. The other relevant thing to notice here is that ID is a primary key column. Let me quickly query this table. Initially I had told that the order will be 1, 3, 2 for a normal relational table. Let's validate that. So here it's 1, 3, 2. No rearranging while displaying of the data has been done. I also mentioned that since it's a normal relational table that has a primary key index, 2 segments will be allocated, one to store the table data and the other for the index. Let's quickly validate that as well. So first we will check what kind of table this is, whether it's an IOT table. So it's not an IOT table. Let's validate if a user segment was created for this particular table. So yes, we have a segment created for this particular table, regular one. Also, let's validate if a particular segment was created for the index as well. So I'm checking if an index exists on this particular table when we have created the primary key. So yes, we have an index name sys underscore C009538 that has been created. Let's also confirm if a segment was allocated to this particular index. So as we can see, we have confirmed all 3 things. The order in which the results were displayed was not changed because we created primary key on the ID column. We had 2 segments created, one to store the data and the other to store the index. And here we are talking about normal relational table. One last vital thing to notice is that when we run this particular query on the normal relational table, we are going to have 2 IO operations. First, we will have a index unique scan, and then we will have a table access by index row ID. So for a normal relational table that has a primary key, we are doing 2 IO operations in this particular case. We claimed when we run this particular query for an IOT table, it is going to do only 1 IO operation. And if we have to execute this query for a million times, imagine the kind of IO operations that will be saved if we use an IOT table. Let's validate all our claims for an IOT table. So I'll create the IOT table 1, and here also we will insert the data in the same order, 1 followed by 3 followed by 2. In our normal relational table, we were getting the data in the same order 1, 3, 2, and we have claimed in IOT the output will be 1, 2, 3. Let's verify that real quick. So here if you see, the data is sorted and displayed on screen, and this is because IOT stores the entire data in the form of a BTree structure. Let's validate that real quick. First we will verify what kind of table IOT1 is. So IOT1 is a IOT table. Let's see if a segment has been allocated for this particular table with the name IOT. I have claimed that no segment specifically will be allocated to the table. Let's validate that real quick. So no user segment has been allocated. I also mentioned that we will have only one segment and that will be allocated corresponding to the index. So let's verify if index was generated. So indeed we have a IOT top index generated on the table IOT1. Let's verify if a segment was allocated for this particular index. So indeed we have a segment allocated to the index of the IOT table. One last very important claim that we have to verify is that when we store the data in IOT table and it is retrieved by using the primary key, we will have only one IO operation against the 2 IO operations we had in the case of normal relational table. So here when I run this particular query, we should have only one index unique scan and no table access by index row ID should happen. So you see that is the case. And as I said earlier, if we execute this for over a million of time, imagine the amount of saving that we will have while the retrieval of data. So here we have the syntax for index organized table, and there are three keywords that we should pay attention to. We have already discussed organization index. Now we will discuss what is including and overflow with the help of an example. So in IoT, when we have overflow and including clause, only the primary key and the columns that are part of the including clause are stored together in a IoT type index. The rest of the columns are moved to a different segment. Now, why would you want to do that? If you have columns that are not going to be accessed frequently as a part of your data retrieval, you may want to move them to a different segments in order to have faster query retrievals. So here if you see, our key is ID and we have explicitly specified that we want to include name as well. The salary part has been overflowed to a different segment, which indicates that when we specify overflow clause, we will have two segments created instead of one. Let's validate this real quick. So I have created the table. I will be inserting the data now. The ordering will remain the same. It should be 1, 2, 3. So that is correct. Now let's see what kind of table has been created. It's an IoT table. If a user segment has been allocated with the name IoT, that is not the case. Let's validate if an index has been created. The index is present. That's the index name. We will quickly verify if a segment has been allocated to this index, which should be the case. So here you see that an index has been allocated, and if you see here, we have an additional segment that has been created, or you can say a new table with the name sys IoT over 75658 has been created, where the overflow salary will be stored. So here we have two segments, one that will store the ID and the name which is accessed frequently, and then we will have the IoT overflow segment where we will store the description. Few more things that you need to know about IoT is that it must contain a primary key. In IoT, the rows are accessed via logical row ID and not a physical row ID. In heap organized table, we have a specific physical row ID associated to every row, which is not the case with IoT table. You cannot have a IoT table in a cluster. Another important point is you cannot use alter index to modify the IoT index property. You will have to use alter table command. Now, as far as the advantages goes, we have already discussed faster retrieval of data via primary key access. We have also discussed, since the index and table are stored in the same segment, the storage space used is less. Another important point is, since the data is sorted in the order of primary key, you can use compression methods as well. And the last important point is, since IoT use logical row IDs, the indexes don't become unusable if the table is reorganized. So guys, that will be it for today's tutorial. I have a small request. If you have not subscribed to my channel already, please go ahead and do it now so that you get a notification every time I upload a new video tutorial. Also, if you feel that today's video was helpful, please like the video and drop in a comment so that I can make more similar content. If you have any issues or concerns regarding today's video, please do drop in a comment. That actually helps me improve my content. Thanks a lot for watching this video, and I'll see you in the next one.